yes, yes.
Okay. Now I start from where Obijit stopped. Actually, it is a program written by Obijit. I did some extension. I did some sort of plots of the data, and as Obijit said, that I actually borrowed the file from Obijit and did my few plots of my kind, and I do it every day. I click this site where it is open. I mean, this Johns Hopkins site. You can see the Johns Hopkins site, and every day I can download these three data. The Obijit says the confirmed, death, and recovered. Every day I download the data, and the first thing is actually Obijit's program. But so I just run it to see what did I plot here. So now it is 142th day. Obijit, as Obijit explained that initial few days where there was no data, so I started from the 12th day. So starting from the 12th day, it is 142th day. Today is 142th. Yesterday's data. It is 142th day. And what did I plot here is first the cumulative linear. Everywhere you can see this plot. To now we are above 4 lakh, and this is the cumulative semilog. And this is what Obijit has already shown us. The increment, which I did by using diff operation on the cumulative data, and this is dn by n. That is the dn by n is the difference in the increment divided by the total number. So this kind of this plot is rare. I mean, you don't see that plot very often, and which intrigues me that dn by n data, after a few initial fluctuation, is now continuously have a declining trend. Even when we have 4 lakh data, it is showing a declining trend. And this is one example is cumulative linear, and this is also daily new cases in the log scale. Now I want to do a little discussion like everybody says that, I mean, it's a very common assumption that the number of cases in the nth day and the number of cases in the n+1 day may be depending on each other by a single constant. I mean, the number of cases in n+1 day should somehow produce constant alpha. I don't want to call it R or anything, that epidemiologically significant quantity. So if this is so it's a recursion relation, so that we can have a relation that actually, if I plot it in a log scale, that should give me n log alpha into x naught. So if I plot it in the n in the x-axis and log xn in the y-axis, then I should expect that n should be it should be a constant slope, and the slope should be log alpha. So one of the curve is this, which hardly shows the constant slope. It shows the slope is actually decreasing, and I'll show that later on also. And on the other hand, this curve, the dx by x, the daily new case is this. Starting from this assumption, the daily new case placed on the logarithmic scale will also be a straight line, where the slope should be n. Slope should be log alpha as a constant. Whereas you can see from this curve that it is hardly a constant. It is decreasing. And now what I did, I instead of just 1, 2, 3, 4, I pressed the dates over here. That trick is very simple. That Obijit has already told us that the columns, the names of the columns were the dates. So this, if you can see this, the data frame column, when I did the last plot, in the last plot, what did I do? In the x, I plotted that after plotting that, I mentioned that the ticks, that I should start from the first day to the end of day, but in an increment of 20 days. and I should label the dates as from DS. DS is the dates. So I use the dates to label my x-axis ticks so that I can read the dates. Now I can read the dates over here. And what I mean to say that, see, the lockdown started from this point. And everybody expects that from lockdown, I should have a reduction in the slope of the curve, definitely. But the point is that the reduction effect should saturate within a few days, say 5 days, 7 days, 10 days. But the trend shows that it is slowing down. The slowdown tendency is continuing despite of the relaxation of the lockdown. This is continuing. So this is something, I don't understand. This is something which intrigues me, that the slope is still decreasing. I mean, although I don't see in this curve, I expect that when the lockdown starts, there will be a reduction of the slope. And then when the lockdown is relaxed, their slope will now increase. And so I should see the inflections in this curve. Instead of, I just can't see any such signature in this curve. And see the dates. It is somewhere here the lockdown started. It is 30th March. It is 5 days before the lockdown started, and then lockdown 1, lockdown 2, lockdown 3. I mean, the different phases of lockdown and the relaxation doesn't. I can't see them on the curve. I mean, there is no inflection or anything. Now, this is another curve. This is nothing. This is more interesting. I just wanted to see the state of Pakistan and India side by side. Red is India, green is Pakistan. And only thing that instead of the total number of cumulative cases, it divided by the total population. So I wanted to see the infected cases per million. So here it shows that Pakistan is in a very bad condition relative to us. Okay, now here comes the interesting point. I started from the lockdown days. I selected March, and then this portion in the log scale, I wanted to be sure about the reduction of the slope. So this is the initial, I fitted a curve for the initial 10 days. This is the curve, straight line for the initial 10 days. And this is for the, last 5 days. So you can see that this is the latest curve. This is the latest curve, today's curve, yesterday's curve. You can see a continual reduction of the slope despite of the relaxation of the lockdown. So something that is, I don't understand, it confuses me. And now, once I can estimate alphas from here, I can make predictions from here after 10 days or after 30 days what will happen. So for example, if I say after 10 days what I can expect, that will give me the values like that. See, this is 1000, this is 1000, 5,87,000 will be after 10 days, according to this approximation. And this is, if we do the prediction based upon our initial lockdown, depending upon this slope. So these are the predictions. Now, most interesting thing is the next curve, where I assume that instead of this recursion relation, where xn plus 1 is connected with xn by a constant alpha. See, this was my recursion relation that I assumed. Now people say that today if you get a case, confirmed case, maybe the person is actually infected 5-6 days before. So I mean, the number of cases that you see today, mostly they were infected 6 days before. So actually this relationship should be xn plus 6 is related to xn. So I just wanted to verify that. I just got the ratio xn plus 6 by xn. And that is very easy when if you do it with Python, just shift it and divide it. So if I do that, see, I just shifted by six places and just divided the whole thing, and I plotted that. So this the RD is just I shifted by 6 places and divided. So it is always giving me the ratio between n plus 6 divided by xn. And what is this? This is, I explained in my previous class, this is a 3-point rolling average of that. So if I run that, I get very interesting curves. This is the x n plus 6 divided by xn. If I call it gamma, it's a plot of gamma, and this is the same plot of gamma with a rolling average. Now this is a high peak, so, and this is before, of course, lockdown start. So I rejected that. I plotted the later portion of that, the portion where the lockdown started. Now this I think is a very interesting plot. I can plot it separately also to okay, now let it be here. Now I call it a very interesting plot because you can see that here there's a declining tendency, but again there are some peaks over there. Can you see and see the deaths? Here the lockdown started at this point, and there's a rise, and then it falls. There's a peak around here. Can you see? It is the last week of April. There's a peak where we thought that the migrations have started. There's a small peak over there. And what is this? This is where the 17th or 17th or 15th of May onwards, when there's a lot of relaxation occurred. There's another small peak. And then there's also many unlocking. So there is a bit of a peak kind of thing. So, but the interesting point is that there's an overall declining phase. Although there's a small peak, and the peaks are of smaller height, and there's an overall decay in this gamma curve, gamma constant. Okay, and I did that with I don't know, and whether it is a.
Arunabha, did you check the tail separately? Did you check the tail separately, tail part?
This one?
Tail part from April, 5th April or before that. Last tail part. Check that. Did you check that separately? I mean, whether the peaks are more prominent or not?
I mean, in the this part, the last few days, last few months.
No, from the small peak before 5th April, before 4th May, before 4th May.
Before 4th May, this one.
Before, this one onwards.
There is a peak. There definitely is a peak.
And I want to see the other peaks also here. There
is a peak where the migration started.
Yes.
And there is a peak where the second, the third lockdown.
Yes, I want to see whether the peak is prominent towards corresponding to the tail or whether that is.
I mean, this is where the unlocking started. And you see, but what I wanted to make that I can see the signatures here, and but there is an overall decay.
Overall decline. Okay, now your message is clear. Okay.
And I can see the peaks over there, and I mean we can see
Okay.
And then I don't know whether six is taken arbitrarily. So I made it 15. When I made it 15, I don't get so nice peaks like this thing. It is a raw, it is a 3-point average. I don't get much interesting signatures or peaks over there. Okay. And then, so this is nothing interesting. It is a 1/15th of that. And these are the predictions that I can make. Now, this is very interesting. This is the death in India divided by confirmed India. That is something which they called the case fatality ratio, that the number of deaths divided by number of cases, the plot of this. Now the plot of this is was showing a decay, but quite recently there's a peak. I don't know why there's a sudden peak, and again there's a tendency to fall down. But this was very interesting when the ratio was falling down. But the
recent peak most likely is because of the Maharashtra death audit. Maharashtra, there is a death audit committee, just like almost everywhere. Ours got a lot more that press,
Maybe,
and the
maybe
death audit
maybe
committee
that is why.
very recently declared a large number of previous deaths as COVID deaths.
Oh, I
So
see. That is
that's
why
why
it
on one
increased.
day the number of total death counts by COVID went up by 1,000 or so.
I see. I see. I see.
Oh, I see,
But
I see,
what
I
I mean
see.
to say
Yes,
Okay,
it's still
that
there
is
diagnostic
the
data.
case.
They're all old
what I
deaths.
mean. Yeah, but what I mean to see that there is always a tendency of decline. There is a rise, and I'm sure that this will also show
I
that
think this will
decline.
fall again. This will fall again, I think, right?
People fall again. That is it.
Yeah,
And
yeah. That particular thing is more or less an accounting problem.
and this is the number of confirmed case by the number of active case, and this is the same thing in the log scale, and this is the what you call the dead by dead plus recovered. Dead by dead plus recovered, the number of closed cases. I mean, it doesn't make sense to consider the CFR where you consider the high number of cases present today, but those who are dead, though they have been detected a few days before. So the more meaningful quantity is the dead by dead plus recovered, the number of among the number of closed cases, which fraction is dead. And I can see that here also that there is a declining tendency till today. Overall there is a declining tendency, and so that is something that is good. Now I will show you something more, that this thing that the curve, I mean, this was haunting me. Why the slope is not exponential and it is still showing a continuous kind of decay. Then I chanced upon a site by where the Nobel Prize winning chemist uh, Michael Levitt, he was discussing the case, and he says that he believes that corona infection is not corona. Most of the diseases are not actually exponential; they are sub-exponential. They are sub-exponential, so it's a very interesting topic. And then this is an interesting article. One can read that. Then there's a YouTube video where Michael Levitt also says that instead of instead of trying to fit it with the exponential, rather we should try to fit it with a Gompertzian curve. So I tried to fit it with the Gompertzian curve as suggested by Michael Levitt, and this is the curve fit that already I discovered, and this portion is reading the data, and this portion is fitting the curve fit that I discussed the other day, and this is the Gompertz equation. If you can say that this is the Gompertz equation, which is a into e to the power minus b into e to the power minus c into t minus t0. So I have the constants like a, b, c, and t0. These are the parameters I have to estimate by fitting the curve. So I tried that following the suggestion of Michael Levitt, and when I did that, uh, the LC is not defined. So this where del C is, oh, it's better that I think now this will be. Yeah. Now this is, if you can see, this is the fit with the compression curve. Apparently, it is a not bad fit. I mean, the blues are the data point of the confirmed cases, and red line is the fit with the data. So till today, and this is in the log scale, which shows that there in the initial portion of the days there was some mismatch, but in the later phase it rather follows Gompertzian equation more or less correctly. And this is, again, I saw this data with the daily new cases, the same fit. I just differentiated that data and said the daily new cases in the log scale, daily new cases in the linear scale, and how the Gompertzian equation fits that. I mean, it's the same fit, just plotted in different windows. and then I extended that to some future cases also, and that future is very bleak according to that, because this will saturate. It is still not showing a saturation at 350 days starting from the start of the lockdown day, and it is over 40,000 or so. And if I say the daily new cases will peak around 150 day, 50th day, starting from the starting from the day of the lockdown. So so if I say, for example, actually ask what is the np.arg arg max of, say, BC, that will tell me when the uh, and also is -1. We do that days. Of arg max. Okay. It shows that the today is the 87th day starting from the day of the lockdown, and the peak is if expected at 153rd day. So 13 plus 53, it's more than 2 months away. And what should be the peak value of this daily new cases at the peak is this, according to Gompersian Fit. This is 23,754. So it's a very bleak situation. But then if you allow me for a few 2-3 minutes more, that I can show you something more. Yeah.
Sure.
This is what. Can I continue for five more minutes?
Sure.
Yes, sure.
This is about people already talk. I mean, every time people talk about this epidemiological prediction, they talk about SAR model. So I'm not going to the exact SAR model. I'm going to present my 2-compartment SAR model, which I want to call a toy model. It's not a realistic model. It's a very simplistic toy model, like a one. I mean, everything is simply. I mean, with a lot of assumption, simple assumption. I just made everything very simple. So as to give us a flavor of the SAR model. In the SAR model, what is done? Can you see that the population is divided into several compartments? Like the first one is S. S is susceptible, that anybody who can be infected with corona, who is not yet infected, but can be infected with corona. And in my model, I get another compartment, I. I's are who are infected but not yet confirmed, and therefore not yet isolated. So they are the ones who are going to spread the infection. They will interact with the susceptible and spread the infection, right? And I assume that there's a third compartment who's a C who are confirmed by the test and they're isolated. So, and I make a very strict assumption that once isolated, they cannot spread the infection anymore. So it's a very, I know it's a bad assumption. There are many reports of infection coming from the hospital. Doctors and nurses are getting infected from the COVID patient, but I just neglected that. Once isolated, I think it's an ideal isolation. There is no infection from the C group. So only infection spreads through the interaction of S and I. Okay. And only the C group is visible. I can't see the I group, the infected, but not visible. Okay. So what should be the dynamics like? This is the typical form of the SAR model. They describe everything with a series of differential equations. This is a typical SAR model equation where I assume that first look at the second equation, the way the infected number is changed. There is the number of infected changes due to the interaction of the infected and the susceptible. They interact with the constant alpha and they increase the number of infected. And now once one is infected, I assume there are two things can happen to him. He can be detected and placed to the third compartment. This is my beta 2I, and the other thing is that he can recover. Within after a few days he can recover. So that is something which I call beta naught I. Beta naught I is a silent recovery. I mean, because this I group is not reported, so beta naught I is a silent recovery, and which I assume that there is no silent death, because in today's time, when there are lots of media always searching, if there is a report in some area there are many deaths in an unknown disease, we will know that. So I can safely assume that there is not significant number of silent deaths. So then there is silent recovery, and I kept so that is beta naught. So now, therefore, the lockdown can definitely affect alpha. Beta 2 is my testing rate, the way I'm testing, and beta naught is something that depends upon biology. I mean, how many days it takes to recover. Now, alpha definitely can reduce the due to lockdown. The point is, therefore, now I will make an assumption that, see, today we have 4 lakhs of infected people, and the population of India is 138 crores. So compared to that, even stable pool is something like an infinite source. So DSDT doesn't change. S doesn't change. S is a constant. If I do that, then this alpha S becomes a constant. I call it beta 1, and therefore the second equation becomes beta 1 I minus beta naught I minus beta 2 I. So it's just a simple exponential growth. I should have a constant exponential growth, and putting that, C will also have an exponential growth, which definitely it is not. We have seen this to curve. It is not an exponential curve, and the curve, these things we have seen. So that tells me that this beta naught minus beta 1 minus beta 0, the effective constant, effective exponent is a time dependent one. There is some time dependence in the effective exponent, and which one can be the cause of the exponent. So I believed, I mean, the simple assumption, the government is always saying that they're ramping up the test. So I believe the beta naught being the testing factor. So I assume that beta naught is actually changing with time, with a linearly changing over there. That is something that they assumed, and therefore I can fit that quantity. The only difference is here that it's again I want to fit the data, but in the only problem is that my model is not a simple equation like Gompertz equation. I call a differential, I call C model. C model is here. The function I have to, this is the fit function, where this is my X, this is my Y. Now with the number of days I want to fit the data, but the function is C model. Look at C model. C model, in fact, doesn't give you an equation like Gompertz equation, but in turn calls a differential equation. The differential equation is given by this, which is that model that I described. So see, every time it takes some values of the parameter and solves the differential equation, and with the solution it compares the data. If not, it changes the values of B1, B2, B2, and see, I can prescribe even the bounds that I want on the parameters. I don't want these parameters to be negative or so. So I clearly said that they should be positive parameters or so. So I did the fit, and I want to show you the plots. This is where this is almost the last thing. Now, here I can also show that after fitting, this is also not bad. I mean, visually, at least you can see that this model, although very naive model, but can, I mean, fit this. Although I don't want to, nice to see that even this naive model can fit my data. This is the fit with the, I can see this fit in the semi-log plot, and even it is better than the Gumpertian, because the initial phase is also, I mean, better described. And this is the growth of I, the invisible spreaders, how they will behave with time. And now after this fit, what I did, I extrapolated that to the future. And so this is how the I group, the infected group, will behave with time. And this is how the uh, C will behave, the number of cases. And the good news, I mean, this is a better, because 17 lakh 50,000 is where it should stop, according to this naive model. It should stop at 17 lakh 15,000. It should saturate. And the delta C is I mean, I don't have any significance, but this nice model says that the delta C will get a peak around 100 days. And this is how the plots of the daily new cases in the logarithmic scale and in the linear scale. And this says these two things. Today we are in the 87th day. Sorry. Oh, what did I do? Okay, doesn't matter. I can. Today we are in the 87th. I know. I mean, I have to get back. Yeah. Okay. Today we are in the 87th day. So today we are in the 87th day, and according to this prediction, there will be a peak around 111. I mean, it's just not very far. 13 plus 11. So it's not very far. 13 plus 11 is something like 24 days. After 24 days, we're going to see the peak, and the peak value is 17691. But absolutely no value to this very toy kind of model, because if you do the fit to tomorrow, you will get completely different estimates. For example, I did on the data of 16/6, the peak was here. The prediction was this. On the data of 26, the peak was here, and the prediction was this. And I mean, this is not very different, but I'm doing it for a very long time, and see that whenever I do it after, say, 10 days, I see a very different prediction. So these predictions are not to be taken at all with any seriousness. It was just a fun to amuse myself, or rather scare myself. But this toy model is not correct, because if you do the fit after a few days, you will get different predictions. Secondly, test is not being ramped up in many states, so my assumption falls flat. And as lockdown is slowly withdrawn, there will be a slowly increase in beta 1, which I completely neglected. But if you really want to see a real kind of ACIR model, one should see this kind of a site where people are trying to model things more seriously. And these, I mean, the predictions that they are doing can be taken with much seriously. I mean, my thing is just a kind of my personal playing, and I showed you just to convince you that this is the power of Python, and yeah, this is the power of Python, and I mean, I can play and do different kind of things with the data. That's it.
Thank you,
I
Arunabha.
just wanted to sort of advertise that many of the people who are working in indiscov.in happen to be my colleagues at ISA, various ISAs, even mine in Kolkata. And they have rather nice models, which are scary, but not perhaps as scary as the compounds.
But no model is actually kind of taking, I mean, you cannot take seriously, right? No model is actually following.
No models
Every model
cannot
is
be
giving you
taken
different
seriously
results.
except for general trends.
Okay.
The whole point is, if you take a model too seriously as far as numbers are concerned,
Yeah.
that by the way, even if you look at the indiscov.in predictions and read what they're saying rather than just look at the headlines, you will see that they clearly say that these are the models, these are the assumptions, and these are places where the assumptions could fail. Look,
Enough.
epidemiological
Enough
models are
reason to be confused.
very old subject. People have done that for a long time. the only problem really is that this is a situation where we don't have enough data at all. Old
Maybe
epidemics have very much of data, and we know exactly how things are going to go.
you cannot believe it in most of the time.
I cannot believe the data.
You can get the trends out of this at best. You cannot get numbers. All those. And so the trouble is, very often you see the headlines in newspapers just from the numbers.
Arunabha,
Yes.
can you test this model, your toy model even, for other countries which started earlier and which have the complete data? For example, some European country, or say China or Japan, something. Can you test this for the country and check?
I was interested in my
Germany,
country where I get to normalcy. I mean, that was the kind of question I was interested in. So
See the
I can do this.
See the Chinese data I plotted is a complete sigmoidal curve, no, right? That is the Gomberg kind of that thing.
Model. When you were presenting, I was looking at it.
Yeah.
And it was really Gompersian.
Yes.
It was Gompersian.
Yes, I'm now interested to fit that.
Gompersian has a slower saturation. It's not symmetric.
Yes, it's not symmetric. It's not symmetric.
Whereas the Gompersian is
sigmoidal. I mean, sigmoidal type. It's not sigmoidal, of course.
Michael Levitt said, Michael Levitt became famous in this field because he could, with his Gompersian idea, could explain the Chinese data very well. He said that it is epidemic.
Okay. Now I get it. Okay. Yeah.
And that I think the people have taken in the field of epidemiology, Michael Levitt CEC, because he could successfully explain with his model the China.
But if you look at his prediction,
China will turn down when the infection number in China will be controlled. He could predict way back in early February. That was his.
His predictions for the rest of the world has gone rather badly because otherwise he would have been out of it by now if you really took him seriously.
No, his prediction was not as bad as Niall Ferguson.
Yeah. Niall Ferguson's was bad, and that was basically because he even got his data wrong. He made a decimal point error, sort of thing. That is bad. Anyway, I think we should call it a day now. And this is.
Thank you very much. And
long day.
What is tomorrow's program? Will it begin with Arunabha's lecture?
No. Tomorrow is
Tomorrow is Anando.
No. I think Arunabha may have some more thing to tell us.
No, I don't have. I can hook up things in a day. So tomorrow we will concentrate and learn a very interesting thing from Anando, that is machine learning.
Machine learning.
Machine learning.
And
machine learning.
What about Roth tomorrow?
Tomorrow is Roth?
Are we getting the virtual papur bhaja?
That you can always get.
So we will import Roth. We will import Hemantidi, we will import Roth. We will import Roth as R. And then we will install that and we will actually use that. Function papur bhaja is a function. So Roth dot papur bhaja in bracket you see. Okay. We will do that.
Okay. Thank you everybody for bearing us, and we will come back tomorrow again at 3 p.m.
Thank you.
Okay. Thank you.